Hello again, Algebra 2. Today we're going to work on lesson 2-3, which is combinations. Just to kind of remind you of what we did in the last lesson, which was lesson 2-2, permutations. We're talking about grouping. So permutations and combinations are both grouping methods. Now permutations are grouping when order matters. Combinations are groupings when order doesn't matter. The examples I gave you yesterday were my pizza example. The first 4 people who walked in the room got a pizza, or a committee example. So if you're going to create a 4-person committee and you have president, vice president, secretary, treasurer, that's a permutation. If you have just a 4-person committee where everyone has the same role and the same power, that's a combination. So if the order in which you get selected doesn't matter, that's a combination. If the order in which you get selected matters, it makes a difference in your life, that's a permutation. I'm going to do a couple of the book examples here just to make sure that we're squared away on this. So lost my page here. So I'm looking on page 729, which is where our homework is going to come from. And problem number 1 says a classroom seating chart. So if we think about a seating chart in like Mr. P's room, we've got my 3 front desks over here and my 2 front desks over here, and then I've got my 3 desks behind and my 2 desks behind, and then my 3 desks behind that, and then my 3 desks back here, etc. And Mr. P's podium is up here and the whiteboard's up here. So the question is, if I put Haley here, or I put her here, or I put her here, does it make a difference in her life? And does it matter who's sitting next to her? And the answer is obviously yes. Putting Haley here is very different than putting her here or putting her here. And whoever I put next to her makes a significant difference on Haley's positioning, on whether or not she's going to be very successful, or maybe not very successful, or maybe her positioning will determine her success. This zone closest to the board may be best for her because she wants to see and hear what's going on clearly, but maybe this is too close for somebody. Maybe they want to be more like here or over here where they have a clear vision of the board but aren't so close. So the order definitely matters. So on problem number 1 in our homework, which is actually problem number 15, our order does matter, so that's a permutation. So problem number 15, which is a classroom seating chart, permutation. Now for 15 through 22, when you're doing permutation or combination, either P or C will suffice. And if you're in kind of a gray zone, there's a couple of them that are kind of like, well, I guess it's dependent on a person's point of view whether or not it really makes a difference. Then you know, I'll okay either answer usually, but if you have questions, let me know, just like always. Now number 16 asks us to find the diagonals of a polygon. Now this is going to come back later, but when we're talking about listing all the diagonals, all possible diagonals in a polygon, let's just use a hexagon in this case. So I have my hexagon here, and I want to create all the diagonals. Well, I need to connect any 2 points that are not directly next to each other, right? So this point can get connected to this point, and this point, but it cannot get connected to these 2 points. Now, the reason that this is going to be a combination and not a permutation is for what I'm going to say next. So, is the combination between point A and point C a different combination than that between point C and point A? The diagonal AC, is that different than the diagonal CA? And the answer is no. The diagonal AC is not different than the diagonal CA, which makes this a combination situation. Let's go back to our seating chart example. If I have 2 seats next to each other, and let's say these are my front 2 seats, this is my board, Mr. P's podium is over here. Is the order John, Haley, Abby any different than the order Haley, John, Abby, or any different than the order John, Abby, Haley? The answer is yes, right? I mean, so even though I'm using the same 3 people in the same 3 seats, by just moving them around within those seats, just like we were doing with the lettering problems in yesterday's lesson, in the last lesson, we have taken and created a whole new combination. JHA is different than HJA, which is different than JAH, and there are actually several different combinations where it's different to go in a different order. That's a permutation. If the combinations are distinctly different, then you have a permutation situation. But if the combinations are not different, then you have a combination situation. So the diagonal AC is the same thing as the diagonal CA. They represent the same line. And there's no difference if you start from A and go to C, or start from C and go to A down that diagonal. Now, again, if this is getting confusing for you, just ask Mr. P, because I think that's probably the most difficult part of the lesson, is trying to determine whether or not they're permutations or combinations. The next chunk of the lesson asks us to just calculate some simple combinations. So C5, 2. Again, when you're doing these, using your calculator, you want to do 5, then go into your probability and choose the NCR button, and then you're going to put 2 on the other side. Now remember, some of you are going to have a calculator that sets it up like this. When it goes in, you'll have to plug in the 2 values when you hit your NCR, and some of you are going to have your calculator set up like this. And the button you're looking for to find that NCR is under PRB. Now you'll find your NCR and NPR buttons there, as well as your factorial usually. So wherever you found your factorial, that's usually where you find your NCR and your NPR. Now again, in the later part of the lesson, you'll be multiplying or possibly dividing these combinations from each other, or multiplying them to each other. Remember to do each chunk either using a parenthesis or separating them somehow between the two. Make sure you're not typing into a chunk. So if you have a calculator that works like this, don't accidentally do something like this where you put your 2 and then roll into your NPR down in it. That's going to really, or your other NCR in it, that's going to really confuse your calculator and mess up your calculations. So if we go through and find 5 NCR2, which happens to be problem 23 in your homework, I go 5, find my NCR button, 2, and then I get 10 different combinations that'll work with that. Now, your NPRs will be much larger than your NCRs, because what they're doing is your NCRs are factoring out all of those repetitious combinations. So in an NCR situation, Haley, John, Abby is not different than John, Haley, Abby, because the order in which people are selected doesn't matter. But in your NPR situation, they are different. So in an NPR, these are two different combinations. But in an NCR, they're one and the same. And so that's what makes your NCRs so much smaller than your NPRs. I'd also like to point out that the book gives equations to actually calculate these using factorials. But the truth is, if you're already using factorials, you're going under your probability options anyway. Use the NPR and NCR button and ignore the equations that it gives you. The only reason you would ever need to use them is if you were moving forward into statistics. Next year, you may have to use some of the equations to these. All right, the last thing we want to talk about are our vertex problems. So let's wrap back to that problem that we were talking about with the vertices. So if I had a hexagon and I want to know how many diagonals my hexagon has, okay, I could sit and count them out. So I have this A, B, C, D, E, F hexagon, and I have diagonal AC, and I have diagonal AD, and I have diagonal AE, right? And then I just continue along the path. However, I've already said that that's a combination situation, and this will work for any polygon that we're working with. So if it's a combination, that means we can calculate it as a combination, but how do we set it up? So we have 6 total vertices on this hexagon because it's a hexagon. 1, 2, 3, 4, 5, 6. Of those 6 vertices, we want to choose 2 of them. Now, why 2? Why do we want to choose 2 of them? Because there's 2 points in each diagonal. So what we're doing is we're using this in a backwards order. So instead of saying how many different 6 groups of, we're doing 6 groups of 2s, not twos from 6. I'm not saying that right, but we talked about this yesterday. It works in 2 directions. What we're doing is we're finding out how many pairs there are, how many unique pairs there are within 6 vertices in this case. And it also takes into account, this will also take into account the fact that the side-by-side ones do not make a unique vertice. All right, so we're going to go ahead and do that. 6 NCR2, and I get 15. There's 15 different unique diagonals in a hexagon. Now that'll work for any figure. Not really sure why everybody's texting me right now. That'll work for any figure that you have if you want to find diagonals. Or you could put other shapes into a larger shape. So if I wanted to find out how many triangles I could make within a hexagon, I could do the same thing. Only instead of doing 6 NCR2, I would do 6 NCR3. Because in order to make a triangle, I need to use 3 vertices. So if I go in and I do 6 NCR3, that finds me the number of distinct triangles that I can create within that pattern, which is 20, which is kind of fun because I can create a lot more triangles within my situation, distinct triangles, smaller ones and bigger ones. Then I can just find diagonals within my situation. I could also find out, how many quadrilaterals that I could make within my hexagon, or how many pentagons I could find within my hexagon. And you could even figure out how many hexagons are within your hexagon, which would just be 1. Okay. Another really important thing to talk about while we're here is the relationship that we have in combination. So I'm going to move back across this and talk about our combination relationship. And I'm going to do so with those sixes that I was just doing. So 6 NCR 0, 6 NCR 1, 6 NCR 2, 6 NCR 3, 6 NCR 4, 6 NCR 5, and 6 NCR 6. So the question is, how many different combinations of 0 objects could I make from 6 objects? So when you're doing an NCR, the thought process, if you're going to pick 0 objects, is usually, well, that would be 0, but it's actually always 1. There's one way that you could pick 0 objects from any group of objects. So no matter what this number is, if you're picking 0, the answer is always 1, because there's one way that you could pick nothing, and that's nothing. Now when you're going to do your NCR 1s, the number of different ways that you can pick one object from any group of objects is the number in the group. So if I'm going to do a 6 NCR1, that's 6. 10 NCR1 would be 10. 20 NCR1 would be 20. No matter what this is, that's your answer. So it's really the other ones that become interesting. Now we've already said that 6 NCR2 is 10 because we had 10 diagonals from 6 objects, and 6 NCR3 was 15. We could find 15 triangles, or was it 20? Just saying. 6 NCR3 was 20. So maybe this was off. 6 NCR2. Ah, yeah, well, this was 15. Okay. So 6 NCR2 was 15, and 6 NCR3 was 20. So now let's do 6 NCR4. 6 NCR4. Well, that's 15. So there's 15 different ways that I could make groups of 4 from 6 objects. And then what about 6 NCR5? Well, there's 6 ways that I could choose 5 objects out of 6 objects. And then 6 NCR6 would be 1. Because there's one way I can pick all 6 objects, and that's picking all 6 objects. Now we got to remember this is an NCR, not an NPR, because the order doesn't matter. Now another really important thing about this, first of all, the pattern, it comes up and then back down equally on both sides. But the pattern also looks like something else we've already dealt with. And this is going to be an important connection when we move further into this unit, because something is going to show up that we had talked about before. Yeah. I lost my zone here. 14641. There we go. And then we're at 1, 6, 15, 20, 15, 6, 1. All right, so if we look at this, this is Pascal's triangle. And this is the 6th row of our Pascal triangle. And this is our NCRs. Every possible NCR from a group of 6. 6 NCR 0, 6 NCR 1, 6 NCR 2, 6 NCR 3, 6 NCR 4, 6 NCR 5, 6 NCR 6. The two are identical. So Pascal's triangle also turns out to be the grouping of NCRs within that given row, which is a connection that we're going to carry forward into some of the later lessons in chapter 12 if we get that far. So it's important to go ahead and make that connection, because Pascal's triangle can save us a lot of time when we're dealing with our NCRs. So if I wanted to do 5 NCR2 like I was doing before, this would be 5 NCR0, 5 NCR1, 5 NCR2 is 10. And that's where I'd gotten 10 earlier from. We'd done 5 NCR2 and that was 10. Okay, none of the 6 NCRs are, but the 5 NCR2 is 10. Alright, hopefully that makes sense, and you'll be able to work through this, but if you have any trouble, let me know. Your homework is problems 15 through 34. Make sure that if you didn't get them, you go back and get 15, 16, and 23 from the beginning of the assignment that I was doing earlier. Have a nice day.